Banded power spectra using virtual channels. Opening an EEG data file from the Spike2 data folder. We will be looking at the portion of the signal's energy falling within given frequency ranges. Double-clicking the channel title, I can see that the sample rate is 1 kHz, much higher than is necessary. I'm going to reduce the sample rate to 100 Hz using the channel processing options. Right-click on the channel to access these. The reason for this is that the power spectra will display frequencies up to half of the sampling rate. Now at 100 Hz, as shown in the channel information dialog, you might notice there is little change to the waveform shape. Ideally, we would have filtered this data to ensure that there are no frequencies present which are greater than half of the new sampling rate. A digital low-pass filter can remove these higher frequencies. Right-clicking the waveform to access duplicate channel. A second channel 1A is now displayed. Notice the original channel number 1 is displayed in red. This indicates that it has a channel process applied. The duplicate is at the original 1000 Hz rate, so I will downsample this to match the 100 Hz required. Right-click, channel process, add downsample, choose one sample in 10 and apply. Now to display the duplicate as a sonogram. This is one way of displaying the frequency components of the signal. We use channel draw mode for this. Select sonogram from the drop-down list. We can now specify the fast Fourier transform resolution of the display. We use the FFT to convert the waveform data into a power spectrum. Sonogram mode shows how the frequency content of the waveform channel changes with time. The sonogram is made up of slices of power spectra. As we zoom into the display, you can see a denser section of power rising from 0 to 50 Hz. This is caused by a fast spike at around 57 seconds. Now to banded power spectra, a display of power in a specified frequency range. From Analysis to Virtual Channels, create new channel. V1 Virtual and a dialog containing the parameters and expression used to create the virtual waveform appears. With Match to Channel, we can set the sample rate for the output based on an existing channel or use manual settings to define a rate. Here I have chosen 4 Hz as the output. The virtual channel is empty until an expression describing what is to be calculated is produced. An expression could be as simple as channel 1 plus channel 2. On the right is a button to help us produce the expression and also restore previously used ones. For our purposes, we use spectral functions, then power in band. First, we choose a channel to obtain the power information from. Next is the frequency resolution that we can tolerate. Now setting the frequency range that we wish to see. I'm using 0 to 8 Hz. We could also see a ratio of powers if we select the checkbox for divide power by power in band. As we complete the dialog entries, the expression is being built and displayed. After pressing OK and then optimizing the virtual channel, we can see the result. The waveform we now see is the total measured power in the range 0 to 8 Hz. As you can see, there is little activity in this frequency range from 32 to 46 seconds. There are increases in power corresponding to the peaks in the original waveform though. To help illustrate what is happening, I'm going to run a quick script. I've stored this script in the script bar for easy access. Now the script is running, it produces a power spectrum of channel 1 on the right-hand side. This is displayed in blue. The red portion is a display of the summed values of the bins in the 0 to 8 Hz range. As I move the cursors in the data view to the peaks of the waveform, you can see the power content increasing. Zooming in to the 8 Hz boundary of the power spectrum, and now setting the y-axis to logarithmic. You can now see that the 8 Hz boundary is bridged by a histogram bin. Do we assume that power is evenly spread over this bin? Unless the source waveform was sampled at a power of 2 data points, then the histogram bins will not align, and we should make no assumptions. Banded power spectra does its best to provide the area under the spectrum that you have asked for. Virtual channels are of the real wave type. They are stored in the resource file that accompanies the data file. They are created whenever the data file is reopened, but otherwise behave just like a waveform channel. Because of this, it is possible to locate features in the data using active cursors or import to memory buffer options. Here we are marking every upward stroke exceeding a level of 5000. This can help with analysis such as sleep scoring. Creating a second virtual channel now. Setting the output sample rate to use. And once again defining the expression. This time a frequency range of 8 to 16 Hz. Pressing OK produces the new trace. As we now have 2 virtual channels, we should title them. Clicking Channel Information, we can access the title, comment and channel scale and offset items. We can also define the y-axis units here. To change the title of the first virtual channel, we can double-click on the existing title. The same channel information dialog then appears. To the color palette now. Here it is possible to change the channel primary and secondary colors. With both channels titled and colored differently, it is easier to distinguish between the 2 displays. As you can see, the blue trace representing 8 to 16 Hz shows different areas of activity to that of the 0 to 8 Hz channel. That completes this brief intro to banded power spectra.